This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
This is a historic moment. I better just fix those lights a little bit somehow. Is that all right? That's all right. You'd think after 12 times I'd remember which setting it was. Anyway, so I'd like to be able to say that we'll just chat for an hour and then go home early, but I'm not going to because I've got lots of interesting stuff to share with you. I'll try not to keep you late, but and some of it I might go through fairly quickly because there isn't too much to absorb. But in this last lecture, again, I wanted to bring together some of what we've been talking about earlier and look at how they are used in particular systems. So what we're going to talk about tonight is listed here. So video calling, and VoIP is a special case of video calling, setting up a point-to-point two-way communicative connection. Mobile TV, although it's not something that's particularly popular, it has some interesting technical issues, and you never know if these, you investigate some technologies and they become unpopular, and then all of a sudden they're used again for something because a new niche comes up. So I think it's interesting to look at that. We'll look at streaming to mobile devices. There was a historical, that's a bit harsh, sorry, but there's been a solution for that developed over many years using RTP type streaming, which is this PSS thing, but we've learned about adaptive streaming recently, and that's really sort of taking over. And we'll finish up by looking at cinema, how cinema has moved into the digital realm, 3D cinema, and cinema sound systems, because that's where the origin of surround sound came from, and there's some interesting technical solutions there as well. So let's launch into it. If I can get this switched around the right way. So, video calling. If you think about what might be required to set up a video calling connection, so what do I mean by video calling? It could be like a FaceTime or Skype type connection, but also could involve conferencing. So we could have multi-party. It could be not just individual devices like handsets, but could be from a conference room or involve telepresence or something like that. But if we want to set up a conversational video and audio connection, what's involved? I'm sure if I gave you 5 minutes and a piece of paper and a pen, you'd come up with a list something like this. But let's go through my list as at least an approximation of the more important things. So obviously we need to be able to input and compress audio and video signals. We recognise that there's a lot of different formats involved though. So we need to establish a call, so that's a telecommunications network function, of course. There's because of the range of different video and audio formats and resolutions and bit rates, there's a need for something called capability exchange. Right? So unless I define for once and for all time that we always must use H.261 video and G711, which is just PCM audio, and we never change, then we have to have some way to accommodate new formats as they come along. And if we have some devices that accommodate the new formats and some devices that accommodate the old formats, then we need this capability exchange feature, which means that we need some protocol by which the two ends must need to agree on what format to use. We need to establish the necessary channels. So do we have a separate stream for audio, separate stream for video, or do we multiplex them together in some way? And we might have to change that allocation of rate during the connection. So for instance, if we have a video conference, then at some stage we might want to send an image between conference rooms. So we allocate rate to that for a little while and then take it back. We of course need to maintain quality of service, so we want to have error protection that's appropriate to the channel while maintaining sufficient low end-to-end delay. And you're familiar now with the importance of end-to-end delay in a conversational service, and we recognise that the error conditions may be different in different channels, if it's mobile, for instance, or if it's a fixed line. We need, of course, to be able to synchronise the media, and we might have to interwork between multiple parties on different devices. So imagine the conference call situation. We could have some people in a conference room, we could have some people at their desktop, we could have several people on their phones, and we might want them all to communicate together. They may not even support the same media formats. So they're the sort of challenges that we need to look at. In terms of standards, you know, I always like to look at standards as a good way of looking at the technology solutions, because A, they're usually widely adopted, and B, they're open, so you can find out everything that's in them. The significant system standard for a video calling application is called H323. I don't expect you to memorise that. It was developed for packet networks, so you know, local area networks or the wider internet, and it will support at least audio, and if the terminals will accommodate it, also video and data. And the intention was that these things would interwork via gateways. So if you have different devices with different capabilities, they'd go via some gateway to translate their formats. It's a packet network interface, so that would be implementation specific in the sense that this standard just says carry this over a packet network, but it's not specific as to whether it's a TCP/IP protocol or whatever. And in terms of the capability that is provided, there's a base level. Despite what I said earlier about needing to negotiate, it's important to have a base level by which anyone can communicate. So if you're an H323 compliant terminal, and you do video, you must do at least H261 QSIF, which is very minimal these days, right? Any device has the processing power and the display capability for that, but there are other formats that you can negotiate. Similarly with audio, this is G711, if you recall, is just PCM, so there's no compression, and you can negotiate others by this signaling protocol, but we're not going to talk too much about that. If I asked you with that same piece of paper, on the other side of that piece of paper, to draw a block diagram of what you think might be in a video calling terminal, then you would probably come up with exactly this. I don't think there are any surprises here. It might look a little bit complicated when you first look at it, but then when you break it down, it's exactly what we would expect. We know we have some video I/O capability. We know we have to have a video codec. Similarly with audio. We've got this block called receive path delay. What do you think that might be there for? Yeah, so the video coding is likely to take longer than the audio coding, introduce a longer delay, so we need to resynchronize. So we introduce some delay. Then we have this sort of multiplexing layer, and as well as our media coming from these directions, we have data applications. This thing, I mean, outside our scope really, I don't expect you to memorise this. This T.120 is for things like electronic whiteboards and so on, that data applications that you might use in a conference. And so those parts are concerned with the actual application, and this part is concerned with the system control. So this is the bit that allows you to set up a connection via the network. So these bits tell the network, I want to talk to this person at this number or whatever the mechanism is. They set up, the connection is set up, and then we communicate via the top half of the diagram. Now this diagram actually comes from this recommendation H323, the one I mentioned, and the network is generic. But if we were connecting such a terminal over the internet, then we would expect this type of protocol stack, as for the reasons that we've talked about before, right? We have a real-time or short delay requirement for the audio and video, so we carry it over UDP, and we would use RTP and RTCP pair to make the best of that connection. The data connections can be carried over TCP because they're not so delay critical, and reliability is important. The control procedures in this video calling application are listed here. There's this capability exchange. I'll talk about that in just a minute. But, well, capability exchange is deciding what capability each of the terminals has, and then mode initialization is agreeing on the first one that we use. And then we might switch that mode between, as we continue through the connection for the reasons I mentioned earlier. If we were using multiple parallel connections, and this is a little bit old really, because we're not going to do it on today's networks, we might have to somehow connect those together. That's what that's for, but I think we can ignore it. We may want to encrypt. We may want to indicate that our terminal or our user has a particular preference for which mode to operate in terms of the audio-video decisions. And we need to manage network addresses to be able to set up connections. So this diagram shows the sequence of setting up an H323 call. It's probably a little bit small to even see, sorry, but I thought it was worth including because it just shows the main stages, and the main stages being we actually set up the connection, so this is network based. There's a gatekeeper there, so something that manages the connections over our network if we want to have the ability to deny connections because maybe there's too much traffic on the network, for instance. So we have this gatekeeper. You have to connect to the gatekeeper and say, can I set up this call? And it says yes. And then it'll set up a connection to the other terminal. So this we're talking between sort of terminal A and terminal B. Then we have this capability exchange where we decide, we negotiate. We say, there are different protocols to do it. We'll talk about one or two. I'm capable of H.264 at this resolution, and I would prefer to operate in this mode. And then the response comes back, well, I'm only capable of supporting H.263 at this resolution, and so on. So we need some protocol to manage that. Once we've agreed on that, then we need to open our logical channels, as they're referred to, which means, okay, I set up this channel for audio and this channel for video. These are the parameters. And then we can exchange our media here. This is our actual call where we've got RTP supporting our media. And then when we terminate, we close off the logical channels and then close the connection down. So there's no surprises there, but it's just worth recognizing that there's a need to be able to do something like this, this capability selection, and setting up channels before we can use them. So capability exchange. How do we actually achieve it? And the quote is often made about standards, and particularly in this space, as we have more and more developments and faster processing and more memory, then we are able to come up with more and more efficient media formats, both audio and video, and so you end up with more and more from which to choose. So there are lots of different formats for audio and video that we could use, and not only the formats, but we could be operating at different rates, different resolutions. and only certain combinations may be possible. So, for instance, if I use an English interpretation of some of the protocols might be, if I use H.264 for video, then that uses a lot of processing power, so I'll only be able to do G711 audio, or some similar example. So it's even hard to say choose from this set of audio and this set of video, because it's actually the combination that might be a limitation. So how do we actually agree between two terminals what they should use? That's what capability exchange is. So in the early solutions, I don't mean to say ignore the standards numbers. I mean, it's just for reference if you ever wanted to find out some more. It's unlikely, I guess. But in the earliest solutions, they had a fixed table of options. They said, okay, this particular code corresponds to H.263 at CIF resolution. So pick that code if you want it, but then it's not expandable, not future-proof. So later solutions, including this H.324, which I've chosen to look at just because it's the modern one that's actually used these days, is that there's a protocol that I didn't think was worth looking at in detail, but there's a protocol that allows us to assign specific identifiers to different formats, and then allow us to communicate this sort of condition. So these are the media formats. Assign them to numbers, and then I can accommodate this sort of video with this sort of audio, that sort of thing. And SIP, which we'll talk about in a minute, which is the more, whereas these, as you would guess, have come from the telecommunications industry. They're ITU standards. The alternative that's come out of the computer industry is Session Initiation Protocol. It's SIP. And these, in a sense, are in competition with one another. They effectively do the same thing. And this one has an offer response protocol. In other words, these are the things that I can support. You come back and tell me which ones you accept, sort of thing. But we'll look at an example of that in a second. So here's the the competition thing between SIP and H.323. H.323 has grown up out of this enterprise LAN solution, application, and there are some doubts. Some people are skeptical that it's really scalable, and it's a vertical specification in the sense that H.323 lists all the all the codecs that it can use and the signaling system that can be used. So it's not just one layer in the sort of traditional computer protocol stack sort of sense. It's also bit oriented, so there are specific bit patterns that mean things. It's not human readable. And it assumes a certain reliability of the underlying network, so it assumes reasonably low error rates. So SIP, as I said, emerged from the computing industry, or the IT industry, and it relies on other protocols like RTSP and this SDP, Session Description Protocol, which we'll talk about briefly in a second. And it's text-oriented, so all the exchanges are human readable, and it uses URLs and DNS and the sort of traditional internet protocols that we would expect. So both SIP and H.323 are used. SIP is quite popular with VoIP protocol, VoIP solutions, voice on IP. And there tends to be a bit of a trend towards SIP, but both are used at the moment. So the SIP protocol stack looks like this. So again, no big surprise here. It's intended to be operating over, or expected to be operating over IP. The media and time-critical components over UDP, and the signaling over TCP. And I mentioned that this SIP uses this request response type of protocol. So here's an example of a SIP request message wanting to set up a connection. And don't worry, we're not going to look at all the components, and I'm not going to give you an exam question that asks you to analyse such a thing. But again, just to understand the principles that are involved. So again, human readable, more or less. So this is an invite message, so it's an invitation for a session. It's asking to connect. It gives the address to respond to. It gives a transaction ID just to make sure there can never be any ambiguity or misinterpretation. What else? Sequence numbers to make sure that we know when something goes missing, and a description of what it is that we are trying to set up when we invite a connection. Uses this SDP thing, this session description protocol. So the session description protocol describes the session. So it communicates when the session will be active. So if you're setting up a video conference between 9 AM and 10 AM, that sort of information is there. It includes the media that will comprise the session and addresses and things like that. Within this media information, it includes the type of media, the transport protocol, the formats, and so on. So a SIP offer answer negotiation could look something like this, very much in English format rather than SDP protocol. But so SDP will say this is the desired communication means, so I want to include audio and I want to include video. You can also use it to include games. What the relevant parameters are, so the codec types and resolutions and addresses, and then the response comes back which of those communication means are accepted. So the terminals might have different, they might be different terminals. As I said, one could be a desktop, one could be a mobile phone, for instance. And the response comes back saying, I can accept these formats with these parameters. And so can we set up a connection? Or it might come back saying, rejecting the invitation, saying, oh, I don't support any of those media types, and so I'll list the ones that I do support, and then so we might have some negotiation backwards and forwards with a retry. So here's an example of this SDP thing, which is describing the session. And you can, I'm sure you can interpret some of what we have here. So we have the media, audio, with PCM mu law, PCM A law, right? Telephony, digital telephone type parameters, sampled at 8,000 hertz. The video is using RTP, and we have H.261 and MPV as MPEG video. So again, the 90 kilohertz clock. And then we talked about 90 kilohertz clock is common for video. So they're the sort of parameters that would be communicated. And I mentioned, when we were talking about RTP, we mentioned the fact that because RTP is specific to the media, we end up with a different protocol for each one. And so this is identifying which one. It's the audio-video protocol something. I don't know the details myself. Then here's a possible answer that might come back, saying that I can do, what's it saying? I can accept the H.261, and I can accept Internet low bitrate coder, I think that is, ILBC, and so we can set up a connection because there's this commonality between the two. So, do I want you to memorize all of this stuff for an exam? Absolutely not. What I want you to take away is just somewhat demystifying this connection, because it's not obvious how you get two dissimilar terminals to agree on how to how to communicate, and this is the sort of protocol that can be used. So these are the standard protocols, H323 and SDP. There are, of course, proprietary solutions for video calling. So Skype uses SIP and SDP, as well as its own proprietary protocols. It uses H.264. I haven't checked to see if it is upgrading to H.265. Interestingly, it uses SVC, Scalable Video Codec. Right? Because why? Because we're talking about communicating between different types of devices with different resolutions and different network rates. And so the scalable video coding provides a somewhat elegant solution for that. They have their own voice coder, which they call Silk, which has a relatively short delay. I think I talked about the problems of UDP and firewalls. Did I? Yes. So how do we get around that when we want to set up a connection like this? Just to remind you of what the problem is, it's that if this guy wants to start a UDP session to here, this is UDP is unidirectional. So this firewall doesn't know that this is coming, so it will just reject it. So the way that Skype works is that both terminals initially are talking to the Skype server, and simultaneously the Skypes, they're always Alice and Bob, as you know. When Alice wants to set up a connection to Bob, she sees that he's online, or the system knows that he's online, and so from this end we just say, I want to connect to Bob, but it's really talking to the server. Then the server tells both of them simultaneously, call Bob and call Alice. And so they both are trying at the same time, and with a little, there might be a couple of retries, but the firewalls know that the received stream is in response to a transmitted stream. And so they can set up their connection. FaceTime is another obvious proprietary solution for video calling. It uses the Apple server in the same way as the Skype server was before. It also uses SIP, uses variable rate H.264, and AAC for audio, and of course RTP for streaming media. So it's one message which I hope you've got from the discussions we had about streaming media is that RTP absolutely, definitely still has a role where we need to keep delay low for communicative media. And so it's all very well to talk about adaptive streaming for video retrieval, but RTP still has a role here, and it's used in modern applications such as FaceTime and Skype. Where we have the issue of communicating between, or interworking between dissimilar services, or dissimilar terminals, I should say, then there are all sorts of issues that emerge, and also opportunities, commercial opportunities. So there are bridging services, right? Companies that set themselves up specifically to provide this bridging between lots of different devices, because we could have, as you see from the diagram, we could have some terminals that just use Skype, and very different terminals that use Skype. You could have, there are what are called telepresence systems, which I'll talk about in a moment. Both Cisco and Polycom provide them. They're the main vendors, but of course their systems are incompatible. This company sets themselves up in the middle there to provide interworking between the two, and translating. There have been some attempts to unify all of these things. Cisco has said, "Hey guys, we've got this telepresence interworking protocol. Why don't you all comply with that?" But there are commercial pressures involved and so on. So there isn't a universal agreement. What are these telepresence systems? Well, they look something like this. They're pretty impressive when you see them. I know superficially you might think, oh, it's just a conference room, a video conference room, but they're deliberately set up such that these images of the people at the remote location are life-size. And they're sitting in front of desks exactly the same as the one that you're sitting in front of, and it very much has the feel of that you're sitting in the same room with them. They're very expensive to fit out. The tricky bit is the audio, maybe not surprisingly, because there are all sorts of issues that you could have with echoes and so on within the room. But you know, major companies have them. I've seen the one that Telstra has at their headquarters. And as I mentioned, the major players are Cisco and Polycom. So a special case of video calling, you could say, would be VoIP. So just the voice component of a multimedia call. But VoIP is sufficiently important that I think we should just talk about it by itself for a minute. So there are lots of different calling products, voice video calling products available that run over IP. Why would you move to voice on IP? If you're someone like a Telstra, this is a little bit artificial because we've now got the NBN, but or even NBN. So if we have a network in place that does constant rate dedicated channel circuit switched digital telephony at 64 kilobits per second, and we've got another network that does broadband packet switched data applications for computing and streaming Netflix and everything else, why would you throw away all the infrastructure that you have for voice and switch it over to this packet switch network, which has problems that we've talked about with regard to delays and packetization and buffering on a packet switch network. And one reason is that it provides a single common network for network and switching infrastructure. So NBN or Telstra or Optus doesn't need two sets of technologies with two sets of staff trained in all those different areas. But rather they just have a single common infrastructure. They can easily adapt across the different loads. So if there is more, you know, you don't have to separately dimension the voice traffic from the data traffic. And they just have one set of switches, you know, one set of routers, instead of having to accommodate these parallel different networks. It also allows for additional features, such and the buzzword or the description for an enhanced voice service is called unified communications, and that means that if everything is IP based, then you can do you can use your PC to control your voice. You can integrate it with contact lists and email and presence, so you can tell if someone's there and so on. But the key issues for VoIP are the establishing UDP connections and the delay, not surprisingly. So this unified communications thing is just a screenshot for the Microsoft Office Communicator product. You know, via pull-down menus, you can make calls to particular numbers, and you can check that the person is present. You know, there's a green if they're present, and so on. It's not very technologically advanced by today's standards, but compared with traditional telephony, it adds a lot of value. And in terms of delay, I guess we've talked about the various components of delays, and so there wouldn't be many surprises here. This comes from an ITU document which investigates the delay components, and we recognise that there are source coding delays and packetization delays, and of course, the network component, the need for a de-jitter buffer to smooth out variations in the packet transfer time. Then we need this playout buffer, right, to make sure that we have our voice data available for the decoder whenever it needs to play it out, and then the actual processing within the decoder. Just to get a feel for the sources of delay in terms of magnitude, this is a rather old paper. I think it was 2002. It's the kind of classic paper on VoIP, sorry. And I think it's useful just to get a feel for the numbers because we might, look at these various components and think, well, we'll spend a lot of time concentrating on minimising something, but maybe it's not a large part of the end-to-end delay. So here, this lists the various contributors to delay, and I think it's just interesting to see which are the main ones. So we see that to smooth out the jitter, or the packet delay variation, requires a buffer at the receiver of some tens of milliseconds. The packetization delay, so just accumulating enough bytes to put into a packet, is significant. The encoding delay, a couple of tens of milliseconds. And when we add all these things up, we get up to about something of the order of 120 milliseconds plus the actual transmission delay in the network. And while we shouldn't think that it's not exactly 120 milliseconds, but it's going to be of that order. Maybe it's 100, maybe it's 130, 140, maybe it's under 100. But the point is that it's a significant proportion of this delay that we saw way back in an early lecture, and saw that we need to keep the end-to-end delay less than about 200 milliseconds, or else it impacts on the user experience. Okay, so I'm ripping through this at a pretty fast rate. I hope that's okay. Just tell me if I'm not making any more sense. At this pace, we might even finish early. I don't know. We'll see. So the next topic I wanted to talk about was mobile TV. While we're in the sort of in the realm of talking about mobiles and voice services, what about streaming media to a mobile device? So, as I said, mobile TV has a specific meaning. It's providing TV-like services to a mobile device. So it's not just retrieving YouTube videos, it's actually broadcasting or providing on-demand TV-like video services to a mobile. Just the fact that we've got a screen, we've got a processor that can decode and display video, people have thought, well, maybe we can actually provide television. And the provision of this mobile TV service could be via a broadcast, a special purpose broadcast network, and in fact that's the one we'll look at in a little bit more detail. Or it could use the existing mobile telecommunications network. It could be unicast, could be multicast, or it could be broadcast by satellite or terrestrial broadcasters. Because it's provided to a small handheld device, so a small screen, and also it's expected to be more popular with short program material. Why? Because you tend, generally you would expect people to maybe use this sort of thing when they're on the train or the tram, or have a short time available, that you're not necessarily going to sit down and watch a whole movie on a mobile phone. So there tends to be slightly different types of programming that's available. Of course, mobile devices, as I'm sure you're aware, have evolved with a very wide range of screen sizes, up to ridiculously high resolutions. So that means that a lot of different types of, a lot of compatibility issues in terms of formats. So where there have been attempts to introduce mobile TV services, they've typically been at sort of low, modest quality, if you like. Not a very high frame rate and only a few hundred kilobits per second per channel. Now I mentioned that mobile TV hasn't been particularly popular. It's been trialled in a few different places. I think it has been trialled here, but it hasn't been embraced. It has been tried in a few European countries as well. And so even though it's not a wildly popular service that many people use at the moment, it brings up a few interesting technical issues that are media related that I thought we might just take a few minutes to talk about. So if you think about trying to deliver a mobile TV, so constant continuous delivery of media to a handheld device, then what are the issues that are going to arise? So one of them is that we're delivering to a small screen, so that might affect the type of material that we deliver. One's going to be battery power, because if we're continuously receiving and decoding and displaying video, it's going to chew up our battery. There's going to be coverage issues, not really media related, but we've got to be able to try to provide connectivity both inside and outside buildings. You know, we can do that successfully with the existing mobile network, but if we were to broadcast from, say, a single antenna within a city, then that could cause reception issues. And we've got a small non-directional antenna, so you know, one of these solutions, the one we're going to look at, is called, what's it called? Had a mental blank. Is DVB-H, DVB handheld. We've talked about DVB-T, DVB-C, DVB-S. There's a DVB-H for DVB handheld. So, and that actually uses a single antenna. In fact, it can share the TV broadcasting antennas to service a whole city. But unlike TV receivers, we don't have a directional antenna, and it's a very small antenna. So there are signal integrity issues that we need to worry about. So just very briefly, how can you provide this mobile TV service? If you were a telecommunications company thinking, I wonder if I can make money out of this service, but I don't want to invest very much in the infrastructure because no one might buy it. So the easiest thing to do is to just use some of your existing mobile communications infrastructure, your cellular capacity, to provide these broadcast mobile TV services. Now, it's expensive in terms of bit rate, but you don't have to buy anything new. So you can try it out, and if no one buys it, then you don't worry. If it's wildly popular, then you find a technical solution that allows you to make money. So wherever there have been mobile TV experimental services, they start this way, just using the unicast connection that is provided by the cellular network. Of course it's inefficient with lots of customers, because if you've got lots of people watching the same stream, but you have a dedicated connection to each one, then you're using up all these parallel connections unnecessarily, in a sense. So you'd like to be able to move over to a multicast model, and in fact that's what is done in this implementation. There's a particular type of service, MBMS. Again, don't worry about memorising these sorts of acronyms, which switch over from a unicast model to a multicast model. So the idea is that you can multicast within the core of the network here if these two cells are provided from this radio network controller, and it can divide the stream at this point, so you only have one connection back to your server. But within the cell, you have multiple channels initially, but when you get to here, described over here, when there are 3 or more terminals in the same cell, then it switches over to a multicast mode, so you all receive the same signal. So it just minimises the redundant broadcast of the same signal. And then there's the third option of going to broadcast. And in that case, we aren't actually using the cellular network at all. We're just using the fact that people have handsets, and we're broadcasting directly from a terrestrial TV tower or from satellite to be able to broadcast our TV services to these handsets. There are, as I mentioned earlier, reception issues, so you might need repeaters, which could be costly. And you might need to have fill-in broadcasts to make sure that you can get reception inside buildings and so on. But it's possible, and there are solutions available. And as I mentioned, and it is the advantage of this system is, of course, that it's completely the costs are independent of how many users you have. So if you have lots of users, then you've got the same infrastructure costs, so you tend to you have a better chance of making money. And that's the one I wanted to just spend a couple of minutes talking about, which is this DVB-H broadcast system. So, and I wanted to look at it because there are a couple of interesting technical issues, and also there's it's interesting to think of how you could best do this. And so the approach that has been taken within DVB is to, as much as possible, make this compatible with DVB-T. Which makes a lot of sense when you think about it, because you can use exactly the same antennas, you can use exactly the same amplifiers, you dedicate some of the DVB-T channels to this additional stream, but the stream has some different characteristics because of some of those features we talked about earlier, the fact that the reception is more difficult, is more challenging, the non-directional antennas, the in-building reception and all that sort of stuff. So it needs more error protection. And we also have this issue of battery life. So where previously with DVB-T, when we were talking about entertainment applications like TV, digital TV, we said that within 7 megahertz, or depends on the country, say 6, 7 or 8 megahertz analog bandwidth, we could get something like 20 megabits per second for broadcast TV, remember? And then there's that whole multiplex, and that could have multiple programs in it. Because of the additional error protection needed for DVB-H, then we only get about half that. So there's lots of error protection involved. So we have DVB-H, which we could put on top of a DVB transport stream. The additional features that are provided for the mobile TV application are a measure to try to save power, which is called time slicing, and I'll expand on that in just a moment. Everything's encapsulated in an MPEG-2 transport stream, but the DVB-H data is actually in IP. So we've got IP packets inside an MPEG-2 transport stream. MPEG-2 transport stream is compatible with the DVB-T transmission. Heavy error correction, as I said, and the input is in IP. So this is what the data structure is. The IP datagrams, IP packets are written into this array, and we have a lot of error correction, so 191 columns of data, 64 columns parity bits, of error correction bits, to try to make the signal much more robust. And in terms of the protocol stack, it looks something like this, where we have the DVB-T transmission. So this is the physical layer. MPEG-2 transport stream we're familiar with. So that's what the television broadcasts also use. Then we have both the application data and the error correction data included here, and the IP packets, the original media come in IP packets. So this time slicing thing, or how to combat the battery drain problem. If we are continuously running our front-end radio receiver component in our handset, then it's a continuous drain on the battery. I should have mentioned, if it's not obvious, that this a handset that is compatible with DVB-H has to duplicate the front end, right? Because it's receiving DVB-T type signals as well as the cellular transmissions. So it's non-trivial to introduce a DVB-H service, because you actually need handsets that are specially built to support it. Another reason why hasn't been tremendously popular. Anyway, if we have this additional front end, radio front end, and it's continuously receiving, amplifying, decoding data, then it's a continuous drain on the battery. And for that reason, there was this introduction of this time slicing approach. So the idea is, as you might assume from the name, that it effectively does TDM, time division multiplexing. So instead of this particular service transmitting all the time, continuously, it transmits at high bit rate but for a short interval. And there's signaling that occurs throughout, so the receiver knows what the timing is of these bursts. So if it's tuned to service number 1 in red, it will receive this service 1 during this time interval, but then it'll shut down, and it'll start up again just before the next red bit of data is due, and then shut down, and so on. And it can, as a result, reduce the receiver power use significantly by about 90%. That's for the receiver part, but I think we need to recognise that the screen would be the main power drain anyway. But anyway, it's just an interesting approach to try to reduce battery usage. And this time slicing also helps with handover between transmitters. So if we had, for instance, a handover between the main antenna and one that was used to infill some part of the city where there was shadowing due to large buildings, then it's relatively straightforward to do it, because we can receive this burst of data from one transmitter, shut down, then wake up again and receive the next one from another transmitter. So it just makes the synchronization easier, or the switchover easier. This plot just sort of gives an indication of the power savings that are possible. So if our burst of transmission, our actual transmission rate increases, then we are using the bandwidth for a shorter fraction of time, and so we save more and more on the battery. And if we are transmitting, as I said, each individual program was something like 300 or 400 kilobits per second, and if we have lots of them multiplexed in 10 megabits per second, then there are enough variable rate streams that we can take advantage of this statistical multiplexing, which we talked about before. So that's also used in the the specifications for DVB-H. So it's just a don't think a waste of time looking at mobile TV. Is even, as I said, even though it's not a service that's been widely successful, but it just throws up some interesting issues, particularly with media delivery. You know, continuous decoding and displaying, and the effect on the batteries, or the amount of error correction that you need to be able to continuously and reliably accept a stream, that I thought it was worth looking at. Okay, mobile streaming. So let's get away from mobile TV, and the difference between the two is a little bit subtle in some sense, right? If we can just stream over our IP data connection to provide something like a mobile TV service if we want, and we can access YouTube and everything else if we want. But what solutions have been developed for this? Well, 3GPP is an industry forum which you may have heard of elsewhere that defines standards for mobile handset service delivery, and it has defined a set of protocols to support streamed media, and it's called PSS, packet switched streaming. There's a particular technical standard for it, and there's no, like as I've said often enough over the last couple of lectures, there's no huge surprise here. It's just interesting to briefly go through the specification and see that it's consistent with what we've talked about. So there are protocols defined within this PSS about controlling the stream, the capability exchange, so the server knows the capability of my terminal and sends me the right stream. The transport layer, how I actually deliver the stream, how I can adapt the rate if I need to, if the reception quality is dropping, and so on. So there are a whole suite of codecs that have been defined within this PSS, many of which should be familiar to you now. So things like remember AAC Plus and Enhanced AAC Plus. You might not remember exactly what they are because you haven't revised for the exam yet, but that's the spectral band replication and the parametric stereo approaches used with AAC. Many video coders that should look familiar to you, still images in JPEG form, of course, and so on. So there's a whole set of potential blocks in this packet switch streaming thing to decode and render all of the different media that we might accept, and appropriate protocols to support them. So video and audio over RTP, all the data-oriented things, the still images, not time-sensitive, and the capability exchange data, the control stuff, not time-sensitive, carried over TCP. Capability exchange in this case is an interesting feature because it's obtained, the capability is obtained from a device profile server. So when I talk to a server and say I want you to stream a particular Big Pond TV service to me, then it interrogates, it knows the device from the request, and it interrogates the capability profile, which is obtained originally from the device manufacturer, and so I know the device I'm on. This tells me the capabilities, so I can make a decision about which stream to send and what resolution, and so on. But it's messy. So, not surprisingly, adaptive streaming is coming to make things easier from the server point of view. So this, of course, as you'll recall, adaptive streaming puts the control in the hands of the handset of the client. So the client says, don't you worry about what device I am. This is the, I see from the manifest that these are the streams available. This is the format that I want at this resolution and this bit rate. Okay, so is mobile streaming all moving to adaptive? Well, that tends to be the trend. MPEG dash is and 3GPP are aligning themselves. So, for instance, there's a just throw up a protocol stack that's defined within 3GPP, and right in the middle here we have dash, which is the dynamic adaptive streaming over HTTP, if you recall. It's the MPEG standard for adaptive streaming. Okay. Right. As you see, I'm trying to provide a taste of all these things and see how all the things that we've talked about kind of come together. So I hope it's making some sort of sense. We're about to move over into the cinema area, so why don't we, and we've been going for about an hour, so why don't we have our one break and do the cinema and cinema sound afterwards. And then I'll just wrap up and maybe talk a little bit about the exam, but I don't want to promise too much. If you've got to look interested and break, otherwise I'll just keep on talking. Just charge this thing.
So this one, first call the server, call the server, and then it means the server in the middle, they will create a connection between
No, it's that they can both talk to the server. Yeah. We've got two-way communication because this one initiates it, this one initiates it, so that's fine. But then the server tries to move out of the connection. It just tells each of these guys to call the other one. And because they're both, we've got two-way communication, we've got streams going in both directions at about the same time. And the firewalls will accept the stream. Because the signal is coming in here, the stream is coming in here, is seen as in response to the stream that's going out here.
But in the beginning, the streams all go to a server.
Yeah.
How the server can make
sorry.
a firewall to go
No,
to
sorry.
connection.
It doesn't tell the firewall. It simply tells this guy
Yeah.
to initiate a connection here.
Yeah. Okay.
Now, if this wasn't, if Bob wasn't trying to call that guy at the same time, then this firewall would reject it. But because Bob's calling in this direction to this IP address, and the firewall is seeing a stream coming in response from the same IP address, then it thinks it's acceptable.
Ah.
It thinks it's just in response.
They use some kind of ice turn and turn technology.
Pardon?
Stern and turn, STUN.
Oh, I'm not familiar with it, but you might well be right. Tell us about it.
It's something like, I was watching through that slide in the last semester.
Oh.
So so these guys will go outside of their firewall, the address, and then they will talk to each other.
Yeah, that's
So they will bypassing the firewall.
and then it's the IP address that's saying it's
Yes.
okay, right?
Yes.
So the firewall sees a stream of data coming back from the address that user is sending data to.
Yes. So basically there is a type of hierarchy of the addresses. So the device will go out of the firewall with some different address, and the same goes with the receiver side. And then those IP addresses will talk to each other. Yes.
一层外壳，把它分成一个包来，可以当一个窗，一个包，然后就做差不多长度。你看这几个是上面对应起来的，这几个合在一起，这个是这几个是那这几个长度就是这几个包的大概嘛，只可以加几个相的，对。就这里，对，但这个是都差不多的。那这个事情要在传输时做，就在传输就是在传输时做。它这个哪做？我们在哪做？我说如果按你这个说法，你这个包的话是，就是加开的就是在传输的时候再把你开开。你问的哪来？要问的。For last lecture here, our question is, what we will do is to combine this package into one trunk and transmit it.
Sorry, what was the start of the question?
And also to describe,
Yeah.
What we do is to, because if we transmit each of these packets, there will be many headers, so it will be inefficient.
And many eye pictures.
And many eye pictures. So what we do is to combine these together into one trunk and transmit. So our question is it happens in the
transmission layer?
Transfer layer? Or the encoding? Only do encoding.
Yeah.
Okay.
Well, encoding, yes. Encoding, because that's where the eye pictures are decided, and then it generates the chunks. And then it's the...
Save into the disk, right?
Yeah.
Okay.
Yeah,
Okay.
right.
So it's not for the purpose of transmission. It's not for. It's for save.
Saving bits.
Save.
Yeah.
No, I mean save in the hard disk. Save
It
into storage.
save storage, but also it saves on the transmitter bits.
对，它 save 可以是因为它 save 的 IP。那很同意。然后，但是它容量，它也减少了容量，因为 IP 取消了，它的容量也少了。它这个少了你的那个就是磁盘的容量成本就少了。你跟他说 save 可以，save 可以好像不会 save。当然是。就是它会变小的意思。不是，它是为了那个 save 在那个翼盘上面一个 chunk。对，就节省空间，节省空间。对。哦，传输跟这个就不一样，它这个 chunk 跟这个传输是没个方式。传输它可以。
Okay, let's get started again, please. So, digital cinema. All the rest of the last part of this lecture is on different aspects of cinema. But let's start by just discussing the move from film to digital cinema, which is relatively recent. I mean, over the last, say, 10 years or so anyway. So cinema is indeed changing from these sorts of projectors to these sorts of projectors. So this is what's in all the cinema complexes around the city these days. Sorry? Well, yeah, but on a larger scale, right? Because, of course, of much larger pictures. So, what's been the driver for that? I think it's interesting to consider what the driver for that has been. So, traditionally, this has been the delivery chain to get movies to the cinema. Of course, the movie was made on film, in analogue form, of course, but also on a physical reel, distributed by truck, delivered to the cinema for projection, and in fact, there were a limited number of films made. So, just want to check what's coming. That's right. So there were a limited number of those physical copies of movies made, and it depended how big a movie it was, how much money people would the movie production house would spend on it, because it used to cost something like $3,000 per copy of film. And if you're thinking of releasing a movie at the same time in thousands of cinemas, that's thousands of times 3,000, so it's getting into the millions of dollars worth of costs just to produce the film. So it was a major expense. It also, what it really caused was the situation where it was just not economically viable to do what is done these days, which is to release globally the movie on the same day, because you would need so many copies of the film. But you only need those many copies of the film for a very short period of time, the first few weeks, and then the interest drops off. You know, many of the people who have seen the film have largely seen it, and of course, as you know, the film is in a smaller number of cinemas and the smaller cinemas for a longer period, but you don't need as many copies of the film. So what tended to happen, and you know, we all know the at least our movie or cinema industry is dominated by the US, by Hollywood, by the major US production houses, and so they would make a certain number of copies of their film. I don't know, pick a number, 1,000, say, and the first release would be in the US. So they'd distribute all these copies of the film via their trucks to the cinemas throughout the US, and then there'd be the big first weekend launch, and after a few weeks, the demand would drop off, and they'd start to get their films back, and then they'd wash them. They'd literally wash them, and then they'd send them off to some other release zone, such as Australia. Right? So we would get the second round of film, maybe with a few scratches on it because of the washing process. So that put limitations on the distribution. It also was a fairly insecure medium. We talked about piracy earlier. If you've got this physical canister of film sitting in the cinema, and you want to pirate something, and you've got a friend who's a projectionist, they could run a session in 2 o'clock in the morning, and no one would ever know. You make a high quality copy of the movie. So,
Just ask you,
sure.
keep saying film and movie. Are they the same?
I mean the same. I'll try to be more careful. When I'm talking about film, I might also be talking about the physical film, but I'll try to be more careful.
Physical film is what? A movie, CD, or?
No, actual roll of film. Yeah. So what tended to, that was the motivation for moving to digital capability. So the first and the major step towards digital distribution was to, instead of distributing the movies on film, to distribute the movies on digital media, so optical discs or hard discs. And they would still be physically transported by trucks, but of course it's very cheap to produce these things, to do digital copies. And then, of course, we rely on a digital projector. Now, without getting too far from the topic of multimedia content delivery, from a business point of view, that presented a bit of a problem, because by moving over to physical media, these guys saved money, but it cost these guys a lot to buy the projector. So this was actually a barrier to this migration for quite a few years, I think, until there was some sort of a business relationship set up where these guys would part subsidise the projector. Anyway, something of an aside. The next logical step, of course, is to move over to networked delivery of these digital movies. Not necessarily in real time, but it could be in real time. So instead of having to use couriers to deliver these physical media, delivery could be via some sort of telecommunications network. So there was I know there was a special satellite distribution network set up in the US, for instance, to be able to deliver movies in digital form to the cinemas, where they'd be stored on local hard disks before they were played out. And this also opens up the possibility for live events, for instance. If you can stream directly into the cinema, then you can do things like sports programs and Olympics and stuff like that. And bring in alternative content, as I'm saying, so opera or whatever performances. I think that figure is probably low now. I didn't check what the current percentage is, but it'd probably be close to 100%. Film distribution essentially ceased by the end of 2013, and this is the satellite distribution solution I mentioned. So this summarises some of what I've already talked about, but why the move to digital cinema? Better quality than 35mm film, offers better security from piracy, it can be delivered faster at lower cost, and allows for other events such as live events and so on to be projected into the cinema. There was also a bit of a technology push, because around the same time Sony and Texas Instruments developed suitable technology to get large screens bright enough and of high enough quality to make digital cinema technically possible. And it's a lot easier to provide 3D using digital projection. And as you know, we talked about the fact that 3D or stereo video hasn't been very popular with home TV, but it's still enough of an attraction that many films, many movies are made in 3D for the cinema. It was slow to arrive for two reasons. One was this business model problem, but that's been fixed, and also a lack of standards initially. So there were different formats, some proprietary formats of the video, for instance, that the industry hadn't universally agreed on. So, not surprisingly, the major movie production studios got together and they formed this alliance to standardise the formats and the exchange that are necessary to provide digital cinema. And they drew on appropriate standards from the SMPTE and from ISO IEC. These are MPEG, of course, or JPEG types of standards. The live event screening has been happening for a few years. I don't know if you take any interest in the World Cup, but it was common to see these sorts of ads around to go and see the World Cup games in the cinema. So it was coming in live and being projected even at strange times like 4:15 a.m. here. What's that? That's the... I can't remember which year was which. Doesn't matter. Oh, there we are. Russia, 2018. Yeah. Anyway, so what does this packaging of digital movies look like? Again, I guess no big surprises about what these blocks look like. We've got an image path here and an audio path here and subtitles here. Captions could be involved or could be available. We've got and then we've got an encryption stage here, packaging up, multiplexing up, and then delivering via whatever means, whether it's by a network or via physical media delivered by a courier. And the encryption stage, of course, means someone has to manage the keys, so you separately deliver and manage those keys securely to the cinemas. And at the cinema end, the flow looks like this. So we've got ordinarily the movie would be stored on local hard disks. And we'd pull off those different streams and send them to the projector or send them to the audio system or whatever. What else? Oh, note, this is interesting as well, note the automation system here. So when you're at the cinema and you see the curtains move to a different aspect ratio, it's not manually controlled from the back, it's all part of the data the metadata that's associated with the movie, so it all just happens automatically. What the media formats? There are two that are commonly used, and you're probably pretty familiar with them. There's the 2K version and the 4K version. 4K, I think, is more common these days. 2K is essentially the same as our HD TV. So HD is 1920 by 1080. You should remember a number, something like that, for HD, and the 2K figure is 2048 by 1080, so almost the same. And the 4K version is up to 2 times as much in both directions. So they're the agreed formats that are used by this DCDI, or whatever the industry forum was called. If you had an odd aspect ratio, and there are all sorts of strange numbers that are, or a wide range of numbers that are used for the aspect ratio in cinema, then you would simply fill one dimension with black. So, or you'd fill one dimension and and black the other one. So we see the example here. If we had 2.39 to 1, which is a relatively common aspect ratio in cinema, then that gives, if we expand it up, if we fill one dimension, 4096, then we've only got 1716 pixels in the other dimension, somewhat less than 2160, and so you just black the other ones, that's all. We can accommodate high resolution imaging in the digital cinema format, so they go up to 12 bits instead of the traditional 8. So we get good colour resolution, and the exact colour space is not so important, it's just another one. Video compression interestingly uses JPEG 2000, or motion JPEG 2000 really, and I would ask you why that would be the case, but I've already given the answer here. You remember what the key feature of JPEG 2000 was? What's the basis of it? What's it built around?
They don't use DCT.
That's right.
They use something a wavelet.
Yeah, wavelet. Well done. That's right. And so the wavelet provides this inherent scalable representation. So it's effectively scalable coding, and it's really easy to extract a 2K version from 4K. So this meant that you only needed to transmit or distribute one version of your movie, and if the cinema was set up for 2K, it could extract that and play it. I've got a graphic that shows this. And if it was capable of 4K, then it could play it as well. So you didn't have to worry about distributing the right version to the right cinema. Very high quality audio, as you see, 48 kilohertz or 96 kilohertz sampling, 24-bit, up to 16 channels, and so on. No compression on the audio. Not surprisingly, a standard such as this for the digital cinema needs to put some limits on bit rates and therefore the capability that's required from the storage in the cinema. So when we allow up to 250 megabits per second for video, 38 megabits per second for audio, as you see, very high rates to maintain very high quality. Then you add up the add up those totals and add some extras for subtitle data and automation data and so on. And the specification says that there could be a maximum of 307 megabits per second for the real-time data that has to be read off the disk. So that allows you to buy and install a suitable disk array. That's the rate that's read out of the disk, but you might not necessarily receive the data in real time, so you might not be writing it in at that rate. So let's say a 3-hour feature, the Avengers Endgame is 3 hours, good example. When you multiply that up, you get 377 gigabytes of storage for one movie. Of course, the other features, right, if you wanted to receive the soccer, the football, and project that in the cinema, it doesn't have to be at 250 megabits per second. You could do it at something like 20 megabits per second, sort of Blu-ray rates or something. This shows the scalability feature. So whether the mastering, the original, is in 2K or 4K version, it can be delivered in the one packaged file, and the inherent scalability of the wavelets allows easy interworking. So if you've got a 4K version and you've got a 4K projector, then of course the flow is direct, but we can easily extract a 2K version from the 4K original and send that off to our 2K projector. And it's just it's a working example of scalable coding. The resolution thing comes up again, of course. Do you need 2K or do you want 4K? And what resolution is needed? Well, it really depends on the viewing distance. And so you know how to do those calculations. Just use the old 1 minute of arc as the guide to the resolution limit for human vision, and knowing the height of the screen, you can figure out how far back you'd have to be before you can just resolve the pixels. This graphic comes from this document from Sony. I should have checked to see if it's still there. But if you're at all unsure about this topic of resolution limits, it's not a bad document to see, to have a look at. It goes through these calculations. Of course, it comes from Sony, so Sony is trying to sell their 4K projectors, so that's why they say, well, you may be able to get away with 2K right at the back of the cinema, but you really need our fancy 4K projector. But the graphics and the explanation is quite clear, I thought. I mentioned that technology push was one of the drivers for digital cinema, so that came from Texas Instruments and Sony. So Texas Instruments in particular provides this digital micromirror device as their means of providing high brightness, high resolution images for the cinema. So they're literally these little mirrors. I don't know if you're familiar with these micro mirror devices, but I think if it hadn't evolved over many years, you would never think of trying to build something like this, but they've literally got millions of these things on the one chip with a piezoelectric controller, and so they can flip these mirrors to different angles to shine the light forward or away, and that's how they get their. So they have a very bright light source shining onto the mirror, and you either project it forward to the screen or not. Sony's alternative technology is the more traditional, I suppose, in terms of liquid crystals. Depending on, well, there are trade-offs as to whether you use one chip or three chips for these high-resolution, very bright images. If you use one chip, then you're changing the image that's on this. This is a TI thing, so it's the micro mirror solution. So you've got this bright light source. It's going through a filter, so you're either sending the red, the green, or the blue towards this micro mirror device, which is projecting the resultant image onto the screen. But of course, if you've only got one chip, then you're only each colour is represented only a third of the amount of time. So these will this solution tends to be a bit more dim. It's harder to get the bright image. The alternative, of course, is to have three chips independently generating the images at one image per frame time instead of 1/3 of an image per frame time. But now LCD screens can even be made large enough for at least small, relatively small cinemas. So cinema projection technology is changing all the time. There's lots of developments there. Okay, 3D. One of the advantages of digital projection for cinema is that it's easier to provide for 3D. It's much easier to provide alignment and synchronization between the alternative views. We talked about the fact that you need to be able to separate the images that a viewer sees if they're going to experience a stereo experience. So you can do that in different ways. Polarization is the most popular. So this can be done with liquid crystal polarization, or it can be done with a spinning filter. So the polarization is different on different halves of the filter. It can be done with twin projectors. So here we have a different polarization filter on each of the lenses. So the polarization, of course, has to use a special screen, a special silvered screen. So if we projected a polarized image onto this screen, which is just plain white, it's like paint almost, then the polarization would be lost. There's random scattering in all directions. So you need a silvered screen to be able to preserve the polarization. This is the idea behind the rotating polarizer approach. So we have a disc that's turning. It's got polarization in one circular direction in one half of the filter and the other direction in the other half. And of course it's synchronized with the images that are projected onto the screen. And the device itself looks something like this. You don't see very much here, except you can see this disc here, which is the actual polarization disc. This is a technology that I'm not aware is actually being used commercially, but it's just technically interesting to look at. So this comes from Dolby, who you associate normally with audio, and they have different coloured filters on the for the two images, but those different filters effectively provide different what do you call them? Primaries. Right? So both images are using red, green, blue primaries, but they're slightly different ones, right? And so we see the left image using one slightly different set of primaries to the right, and they can be filtered out with corresponding filters in the glasses. And the advantage of that system is that you can use a standard screen because it's all based on just the colour filtering. And here we show the wheel with the different colours. Okay, ripping through it, let's start on our last topic, which is the sound systems. And I wanted to talk about the sound systems because really surround sound came from the cinema, and I think it's interesting to look at some of the technological developments in the context of the history of cinema sound. I hope you find it interesting as well. Anyway, surround sound in the cinema is probably older than you would expect because the earliest version was actually back in the 1940s with Disney film Fantasia, if you're familiar with Fantasia. There's the image from Fantasia. And it was an experimental effort between Disney and Bell Labs. And they used 5 channels, exactly what we are most familiar with today, at least in home cinema. Left front, centre front, right front, and then 2 surround sound channels. At some stage we'll talk about why we have that arrangement, in particular the centre front. I think I've got something coming to talk about that. The question is what you do with those soundtracks and where you record them. And at the time, the solution that they adopted was to record those soundtracks on an additional reel of film. So there was one reel of film with the video, another reel with all of the sound tracks recorded on them. They had to be synchronised. You had to have, of course, a special device to extract the audio from this second reel of film. And in the end, bottom line is it was too complex, too expensive, and pretty much disappeared. Then the next time when surround sound became important was in the 1950s, when there was a big, there was an explosion of developments in cinema. Why would there have been an explosion of developments in cinema in the 1950s? History buffs? What started to emerge in the 1950s in competition to cinema? Sorry? I know you weren't around. Even I wasn't around. Well, anyway. Yeah, I know. But you know something of you know something of history. Particularly, you're probably interested in technology history. TVs, yeah. So TV emerged in the 1950s, or late 1940s, 1950s, 1950s in the US, and so. It's all very well with hindsight we can see now that cinema and TV can coexist, but back then if you ran a cinema, if you were running a movie studio, you were terrified, right? Because everyone was going to watch their video entertainment at home and no one was going to come to the cinema anymore. So with that perceived threat and competition between studios, it led to all sorts of big changes and experiments in cinema. So they had huge screens for a while, and they needed many channels of surround sound. So this is an illustration of how insanely large these images were, because they were trying to differentiate themselves from the little black and white picture in the corner at home. And with the big screen came the requirement for more channels. And these additional channels were recorded magnetically onto film. So you needed a special soundtrack that carried the magnetic channels. And again, too complex, too expensive, and virtually died out by the end of the 1950s. Some films continued to be produced with that surround sound, but it had to be on 70mm film because they needed room for all of those multiple tracks, and it was very expensive. So the figure I found quoted was 14 times as expensive as 35mm film. So, and it meant that you had to keep track of multiple versions. So, you know, does this cinema have 70mm capability? Well, yes, okay, I send them this version of the film. Otherwise, I've got to send them the 35mm version, and it just adds to the complexity and risk of mistakes. So thinking about surround sound, why not music and radio? Why only the cinema? Well, it's because we couldn't even record 2 channels on a vinyl record until the late 1950s. And this was the source of audio for radio. Okay, so centre speakers. I don't know that we've had this conversation, so let's discuss it now. I think I've got this these graphics all very well worked out. So imagine you're at you're listening to a stereo music recording of an orchestra from those 2 speakers, left to right, all works well. Then you have what's called a sound stage of music, which means that because of the way it's recorded, I'm not a musician, so cellos maybe over on the right hand side are louder in the right speaker than the left speaker. The violins are louder in the left speaker than the right speaker. So at the front there you get this impression that that the music is spread out in front of you. It comes from different directions. It really is simulated as if it was coming from a stage where the musicians were distributed. But now think about watching a movie with the same sound system. So now when Heath Ledger says, "Why so serious?" if that means anything to you, you want the sound to come from him. Right? You don't want it to come from the outside. So from your point of view, that's great, right? You hear the left and right about the same volume, and so your brain perceives the sound to come from the centre. But from over on the side here, you hear only the right speaker, right? And so you're not getting the right impression. The sound is not coming from the direction of the image. And so, particularly when you've got dialogue, it's the case for the music as well, but particularly when you've got dialogue, in the cinema, you really want the sound to come from the centre because you've got a wide range of people hearing it from different directions. And so that's why, even with that very early Fantasia attempt at surround sound, you have a speaker behind the screen in the middle. And in fact, if you go up to the next time you're at the cinema, you go up to the screen before you take your seat, and you'll see there are little dots, little holes in the screen, right? Because the sound has to project from behind the screen. And when we had that scenario I spoke about, where we have these, the insanely large image back in the 1950s, then you needed multiple speakers, right? So that these guys could hear the audio coming from the correct place in the screen. Dealt with that. So to get a surround sound experience, we need left and right channels so that we get this feeling of the sound coming from the expanse across. We need at least one centre speaker, so that no matter where you are in the cinema, particularly the dialogue comes from somewhere near where the speakers are, and your surround channels, of course, give you that sense of being involved in the middle of the sound stage. Now, in terms of the success of surround sound, it actually finally did succeed in the mid-1970s, and that was with Dolby, so the Dolby name that we associate a lot with audio. And you could have a bit of a debate whether Star Wars was a success because of Dolby Surround, or maybe Dolby Surround was a success because of Star Wars, but that was the earliest major film that used this new Dolby Surround sound. And everyone's seen the original Star Wars, but you know, with spaceships coming over your heads, and it was well suited to surround sound. Why was it a success at this stage? Well, the screens had become a little more rational, so we just had smaller cinemas, so we didn't need those 6 or 7 channels, so we could get away with 5. No, in fact 4. So they used a single channel for the surround sound effects, and then the left, centre and right at the front. And they were recorded optically onto film. So we didn't need the additional magnetic track onto film, so it wasn't so expensive. And another major success factor was that it was compatible with the existing 2-channel and 1-channel equipment that some cinemas had. So again, you didn't have to worry about what the reproduction equipment was in a particular cinema. You could just send off a reel of film, and the equipment could automatically extract a 2-channel version or a 1-channel version or the full surround sound version. So, well, we're still analog. So what about digital surround? There were a number of solutions. Kodak, interestingly, became involved in digital surround sound, digital cinema sound, as early as 1990. But their system, this CDS thing, was only ever used in 9 films, and Kodak withdrew from that business because they were having technical difficulties, and anyway Dolby dominated, because Dolby released their digital surround sound solution in 1992, used 5.1 channels, what we previously described or discussed with regard to surround sound, optically recorded onto film. Because of the available real estate on the film, we'll talk about that a little later, they actually only had 320 kilobits per second available. Why would there be a limit? Well, we're recording optically onto film. The film only has a limited resolution, so you would expect a limited data rate. And there was already a lot of space taken up on the film. There's the movie itself, of course, and also the existing analog soundtracks, which were maintained for compatibility. But we'll talk later about exactly where that data went. Dolby wasn't the only digital cinema sound system, though. DTS you've probably seen in the credits of movies, or on it's also used in DVD, or not Blu-ray, DVDs. Was it Spielberg? Was the director of Jurassic Park? I can never remember. Was it Spielberg or... Yeah, I think it was Spielberg. So he was a major investor in DTS and used it in Jurassic Park. That was the first major film that used it. From the technology point of view, this one was interesting because they recognised that there was this problem of trying to get an adequate bitrate on the film, and so instead they recorded the audio on a separate disc, separate CD, which sounds a bit dangerous, right, because of synchronization issues and so on. But there's a a synchronization track that's recorded on the film to ensure that there's synchronization between them. But that meant that we could use a much higher bitrate, of course. Right? And so DTS will always claim that their quality is higher because they don't face this same constraint. Then there's one additional digital sound system that was introduced around the same time. That one came from Sony. This had an interesting origin. Well, I consider it interesting anyway, because it was essentially a compression system that was lying around and that they didn't have anything to do with. So A-Track was originally developed for their mini disc. So their mini disc was intended to be the replacement to the Walkman, an updated version of the Walkman. So little discs of digital audio, but that was never successful. And so, but they've done a lot of work on this particular audio compression system, and so when there was the possibility to introduce a digital cinema sound system, they thought, okay, we'll use that, and so that was its origin. Anyway, and this was still optically recorded on the film, but only just, as we will see. So, so at the end of the end titles in many movies, you will see something like this commonly, right? Dolby Digital, SDDS, the Sony one, and now Dataset. It used to be DTS, but they just sold the cinema audio component, and so it just has a different name, but that's where it came from. And the codec is just the film, not the audio, because as I said, it was only used on 9 films. So a little bit more detail about those different formats. DTS was the one that is recorded on a separate disc. So there's they were freed from the restriction of only having a limited bitrate on film, and so the bitrate was about 1.5 megabits per second. Remember, the Dolby one was 320 kilobits, so significantly higher bitrate available. And they just needed a code on the film to ensure synchronization, but also it had a code that uniquely identified which disc, so you couldn't accidentally put the wrong soundtrack with the wrong movie. But because they only needed to record a very little amount of data, it was easily applied to any film. It didn't take up much space. And DTS is also used widely on DVDs as well. In terms of the encoding, it's nothing very sophisticated. It's not very highly compressed. It essentially uses subband coding and adaptive DPCM. And there are different versions here, different rates for consumer version versus cinema version, but I don't want to bother going into the details there. At very low rates, having said I won't go into the details, at very low rates they do apply psychoacoustic masking, but at the higher rates it's just ADPCM and subband coding. SDDS is the Dolby one. It's based on like a transform type coder. Does subband decomposition, and each band is differently encoded using a transform. That's all right. That's the basis of it. So, where is the real estate on the film for all of these different streams? Well, it's kind of only historically interesting because film has largely disappeared, but I think it is interesting to understand why the different solutions were driven the way they were, because this is what a length of film would have looked like. It did look like. So here we have the space taken up for the image, of course, and at the side, between the sprocket holes and the image, there was a little bit of space. The original analog surround sound recording was always maintained because it was seen as a fallback. So if everything else failed, you could always get that that surround sound. So when Dolby came along and said, "Okay, guys, we want to put some digital data in there," there wasn't much space left except between the sprocket holes, and so that's where the Dolby data is. So yeah, I've got a blown up version of that in a second. But now that was used, DTS came along and said, "Hey guys, we just need a little bit of data to get our time synchronization." So they've squeezed that time code down there. Then Sony comes along and says, "Well, we need some space too," and so the only thing that's left is out on the outside of the sprocket holes. And what do you think would be the risk there? Is that the film gets damaged. And so there's a redundant track on the other side, and they're actually offset, which is clever, I think. So they're physically offset, so that bit, the audio that's recorded here on that part is recorded down here on the other part, so it's unlikely that they both get damaged at the same time. So if we blow up a section of film, this is what we see. So there's the Dolby recording in here, with a nice little Dolby symbol there. This is the analog surround sound, and these are the time codes for the DTS, and there's Sony stuck on the outside of the sprocket holes. So these days we might have something like anything up to about 8 channels typically in the cinema. And this is where they are, depending on the size of the screen, whether we need these multiple channels behind the screen. We might have an arrangement something like this. But that's not really enough channels, not enough loudspeakers, because more recently we've had Dolby Atmos. Anyone heard of Dolby Atmos? Yeah? So Dolby Atmos, well, it's more recently, it's already 7 years old, and Atmos provides for up to 64 speakers, and their aim is to provide a kind of hemisphere of sound. So instead of having spot loudspeakers in particular locations around the cinema, but always around you, nothing above you, they allow for loudspeakers over the top as well. You can see why Dolby would be interested in this, because then all the cinemas would invest in their equipment. But this Atmos solution is now also available for home cinema. You can have the attraction of Atmos is that it works with as many speakers as you have, and DTS has responded, so they also have a similar kind of solution. What I wanted to show you, if we have the time, if we could just have a look at this YouTube clip, because it comes from Dolby and it describes Atmos, but in doing so it also provides a bit of a perspective by seeing how surround sound has changed over time. So it's 7.5 minutes long, and I think it's good use of 7.5 minutes of our lives, so I might just play that for you if I can figure out the logistics. And turn the lights off.
Dolby's been long associated with audio. We've innovated in the cinema space for over 40 years now. And we're in a unique position that practically no other company occupies. Part of our research effort that's been going on over the past few years was, how can we move sound beyond what we've been able to do today and what would that look like? So when we look at the evolution of sound in film and cinema, we started off with mono, single speaker in the middle of the room behind the screen. Then we moved to stereo. We added 2 more speakers and created 2 more channels, so now we had a dedicated dialogue track, and then 2 additional speakers, the left and right, that allowed us to create a better spread and sense of imaging inside the room. Then it was the evolution and introduction of surround sound that we were able to actually put sounds all around the audience. That surround configuration initially started as a mono channel, so that we were using it as a single source that we sent everything for surround into the audience. Then with 5.1, we were able to split the room in half and now have a left surround and a right surround to allow us to have more sense of movement of sound across the audience. With 7.1, we split the room again into 4, so now we had left, right, back wall, left, back wall, right. So now we had 4 surround zones instead of 2, and that allowed us even more definition. Logic would make sense that the next progression would be like a 9.1 or an 11.1 or even a 13.1. But the feedback that we got from content creators was it wasn't going to be good enough. And that's when we knew we had to make a more bolder step in moving forward. So what if we could start again? What if we could go back and completely redefine how we bring the surround sound experience to audiences? So what Dolby's bringing now is the next generation surround format for the industry. With a channel-based solution as we have today, if we look at how I move something around the audience, in 5.1, we had 2 zones. So if I wanted to create a sensation of movement, it's either here or here. It goes from one side of the room to the other. It doesn't really create that sensation of movement. With 7.1, I can now be on the side, then behind, and then to the side again. So it gives you the sensation of movement, but it doesn't have that precision of movement. So the fundamental shift in what's happening is that now we're migrating away from channels. The ability to move a sound through the room now with objects creates this precision movement, which is referred to as a pan-through array. Now the helicopter has that fluid movement of hitting speaker number 1, speaker number 2, speaker number 3, speaker number 4, and then having that precision as it goes around me in the auditorium. And now by placing speakers over the audience, we can truly create that immersive sound field that now makes it feel like the helicopter is literally buzzing over your head. Overhead surrounds, for the first time, adds that upper hemisphere of sound that we've been missing from films. With the next change of technology that can come to mixers, I think the things that really excites them, especially from a creative point of view, is the flexibility for the first time of being able to unmarry sound. When a film is mixed today, it's made up of many elements, and then all those elements are baked in. You can't go back and pull the ingredient out. But with objects, you could now go back in, remove the object. So if the object was a music soundtrack, we could go in, pull it out, and replace it, and have more finite control and precision in the reproduction of sound. With channel-based solutions as they exist today, one of the problems that we've always faced is how we deliver all of these different formats. If we take 7.1 as an example, then 7.1 is mixed throughout the entire process of a film. At the very end of that process, the mixers will then do another creative pass to take it down to 5.1, because we have multiple playback systems in the world. Now, when they go to a theater, the only control that the mixer has is volume level that the movie will play at and simplistic delay that controls the surrounds. What Dolby's proposing is now they can mix in the biggest mode possible. This now goes out as a single deliverable file, carrying metadata and information that will accurately reflect what the mixer wanted. This dramatically simplifies the entire process. The next generation surround format will have all of this great intelligence and in essence adapts itself to any playback system that's out there. Now we can literally author once and then optimize anywhere. As a moviegoer, you already realized as you go to your local complex, every room is different. Their size, geometry, stadium seating, and And if you're putting surround speakers in there, it creates some challenges as to how you can position them so that you can get uniform coverage throughout the seating area. As we deliver this next technology, that is where it really shines, by being able to accurately portray in all these different room sizes, geometries, speaker feeds. It's a radical shift from anything we've ever done before. For theater owners, their primary concern as always is, how can I get more people to come to my theater? But now, with this better technology of surround sound and sound over the audiences, that now gives them something to leverage bringing people back into the theater. With Dolby's new technology, we're literally building a pipeline for the industry, and we're going to be future-proofing the exhibitor by providing them this technology which will sit with them for a significant period of time. So what we're doing is really a huge fundamental shift in the way audio is not only mixed but also perceived inside your theaters. And it's really a huge change from 5.1 to 7.1. That was only an incremental change. And that what we're giving you the capability of providing now, it's enormous. The ability to have pinpoint precision, the ability to have these sounds wherever they need to be and over the audience for the first time is a real differentiator that hasn't happened before. It's all about the excitement of what audiences will experience, but also just the amount of excitement that you get from a content creator when you walk them through some of the things that we've done and seeing how excited they were about this, then that's definitely worth it.
Okay, so I hope you thought that was worth it. I thought it was quite a good description of how the system works. And interesting, did you hear the terms objects? No? So we talked about object-based coding in imaging and video in terms of encoding each object in the image and allowing them to be rendered. You know, the combination is at the stage where they're decoded and rendered. This is exactly the same thing with audio. You're able to, they were encoding some audio source as an object, placing it somewhere in that field, and then only at the point where you're decoding and rendering do you decide, well, okay, that's at that particular location, so this is how much, what the volume should be and the phase should be for each of the speakers. Anyway, not that I'm devoted to Dolby. As I said, there's a DTS alternative now, but it's interesting. And of course, Dolby Atmos is available in cinemas here. I can't remember them. I know that Village at Crown has it. I'm sure there are others, I just don't remember. Okay. So, question: where do you think that this is? All this data is going to fit on that celluloid film strip we talked about before? It's a trick question. Yeah, instead of the film, you probably need it. No, there is no film strip. This is only for digital. So we're talking only about file transfers here. Okay, so that completes the content for the course, for the unit, sorry. But I would just, before we finish up, I would like to say a few things, just wrapping up the last 12 weeks. We have covered a lot of material, maybe more than you have hoped, I'm not sure. But if I take you back to the first lecture, we saw a slide something like this, and this is what my objective was to cover. So we looked earlier about the particular characteristics of video and multimedia signals, why they had special characteristics that warranted looking at multimedia content delivery as a subject in its own right. We spent quite a long time talking about compression, and sometimes I felt uncomfortable about just how many lectures we were devoting to it, but everything else we spoke about was ultimately dependent on the format of the signal. Right? So how sensitive was it to errors, what were the consequences in terms of delay, and so on. We then looked at the how we multiplex and transport the media streams, and what are the issues with regard to storing in servers. We talked about the content-based issues, the metadata, the managing of content, the issues of piracy. And then what I've tried to do over the last few lectures is look at how all of those technologies and those characteristics impact on the delivery or the design of a solution for delivering over IP, delivering broadcast TV, and the ones that we looked at tonight. So I hope the subject has more or less met your expectations. That was what we set out to do, and hopefully we've done it. If you don't think so, please let me know. So a few words about the exam. I'll distribute copies in a second for those who are here. That's just for Tristan, really. Anyway, the basic format is the same as in previous years. It's there are 40 marks for 20 multiple choice questions, and almost every year, although I say it now, someone will ask me in the exam, can we put more than one answer on one page? You're a very intelligent bunch, I'm sure you'll remember this, but and the instructions tell you. So what I'm expecting is that those 20 multiple choice questions are just put the answers on one page of a script book. I certainly don't expect one new page for every answer. But that's not really important. Then there are 140 marks that are written, drawn, explained, calculated, whatever. There are no penalties on the multiple choice. So if you're right, you get the score. If you're wrong, you get nothing. What's permitted? Almost nothing. Just pens. It's a obviously closed book. You can bring an approved calculator. No papers, no dictionaries. So I will be there at the start of the exam, and if there's anything that isn't clear, I really want you to ask me, because I don't want you losing marks because of maybe a confusing explanation from you or some word that you weren't clear about. I obviously can't tell you how to solve a problem, but if I can provide some clarification, then I'll do so.
Will you be there for 15 minutes? Or?
I'll be there for reading time, and in fact, I'll be there for reading time plus around 30 minutes. I don't know, when questions stop I might get bored and go home, but I'll normally expect to stay for about that. After that time, supervisors can still phone me, but you're giving a message via someone who doesn't understand multimedia technology, so it would be better if you ask a question while I'm still there. You're obviously an intelligent bunch, so you wouldn't do this, but there have been problems in the past that I see where people tend to pattern match. They do some past exam papers and then they see the word term SBR just as a random choice, and they say their brain says, oh, this must be the same as the question that I saw from the past paper, so I'll give the answer without thinking it. So just think. I think your aim should be to understand, not to memorize. I'm not trying to, in fact, I'm deliberately going to be trying to test your understanding, not your ability to memorize slides or memorize particular numbers or standards or something like this. Past exam papers are going to be the most useful thing to try. The more recent the better, because the subject has changed over time, but the last few years are not available. If you've got any questions, then please use the discussion board and please answer one another's questions. It really is important. You can reply anonymously if you want, if that bothers you, but whether you're anonymous or not, if you have the ability to answer someone else's question, then that means you understand something properly, and it's really good exercise. And I'll check to make sure that no one gets misled. I'll contribute as well. I'm most likely to wait a little while before I answer to give someone else the chance. but eventually I'm likely to give in. And I'll participate, just to let you know, I'll participate up until 10 p.m. the night before. It's just so there's a cut-off date, so you don't feel you need to stay up until 3 o'clock in case you miss something, because I mean, you can participate if you want, but I won't be there from 10 p.m. on. If you email me directly and say, can you explain this? Most likely my response will be, can you please put that on the discussion board, because I'd rather answer it once for everyone, or I'd rather have everyone have the opportunity to answer. What's the exam going to be about? Well, let's just discuss this, what my expectations are from what we covered tonight, because I think possibly you're in a little bit of a panic thinking, do I have to remember that SDDS is a sub-band approach and sub-band coding approach followed by transform coding? I've got to remember what the filter cutoffs are. No. What I expect you to take away from tonight is that SDDS is one of the cinema audio formats, and it's going to be reasonably high quality, and you would get it in the cinema, but you probably wouldn't get it in a phone, and you probably wouldn't have an application on a desktop that would support it. So think about what applications could use SDDS. Would you use it in a video conference system? Probably not. So they're the sort of high-level things that I expect you to know. And if there are specific questions about, I hope I haven't asked a question like this, but I could ask something like, I could say SDDS is an audio coding system based on sub-band coding. Tell me basically how sub-band coding works. Right? That's, I'm trying to test your understanding, not your ability to memorize stuff. And I think that's about it. So,
What about the encoder and decoder diagram? We have to memorize all of this.
which?
Decoder, you know the diagram,
Block diagrams.
block diagram.
Well, I expect you to understand to understand that basic structure of image coding, JPEG, what the main blocks are, and similarly for predictive motion compensated video coding, because they're all the same. All based on the same architecture. Any other questions? Okay.
Calculation seems not be there. Just the first lecture was there for the calculation, like the height and the distance.
Yeah.
Otherwise, I don't think there is more calculation.
There's the image resolutions and things. Yeah, maybe, or we talk about we talked about CDNs and having a certain amount of data on the central server and on
Okay.
the edge server, so you might have to stream a certain volume to satisfy certain requirements, that sort of thing. But yeah, most of the interface, is sort of understand the concepts of which is unfortunate, because it's much faster than mark exam papers than calculations. From a purely selfish point of view. Okay, you probably don't want to be kept any later, so thank you very much for choosing the subject. I hope it was useful to you, and thanks for coming along to the lectures.
Thank you.
No, don't apologise. It's a really good problem. Oh, sorry, I should have mentioned something like that. It's purely two reasons. One is that they wanted the scalability, and also they didn't need really high compression. So they didn't need, so they didn't want to bother with frame prediction. So JPEG 2000 is just, motion JPEG 2000 is just treating each frame individually.
So those are, the cinema video, it doesn't do any compression.
Oh, it does.
it does, but
only within a frame.
only in a frame.
Yeah.
Only using like using JK2000 for each frame.
Yeah, that's right. Because they've got huge bands.
So it doesn't
huge bit rate.
yeah. So it doesn't record prediction error anything like that. It doesn't do it doesn't do prediction.
No, it just
But in
does,
frame,
within the frame, it just does this way.
what about the in frame prediction?
No,
Not because they're using the JK2000.
Maybe, yeah.
Sorry, I forget.
Don't worry.
Okay.
Thank you very much for that. Okay, all best.
Oh, I remember now. Just now we're talking about the mobile TV and mobile on-demand stream, right? What's the main difference between these two? It seems like
Sorry,
it's
between what? Sorry?
the mobile TV and mobile on-demand stream.
Yeah,
What's the main difference between these two? It sounds like
it is a bit subtle.
very,
In fact,
very
one of-
similar.
yeah, in fact, one of the
I don't know
mobile
which
TV solutions, I
which
think,
side. I don't know which side.
further. So one of these, I think, uses PSS. Yeah, uses that packet switched streaming protocol. But then this is very different, right? In the case of broadcast. So mobile TV is really more a definition of the service rather than the technical means of delivering it.
Yeah.
Yeah. So you could use this protocol, whatever it is, this thing,
Yeah.
to stream the mobile TV programs over your cellular network,
Yeah. Yeah.
right? Or you could broadcast the whole thing from a satellite. So yeah, there's overlap.
Mm. Sounds very similar. Yeah.
Yeah, well, as I said, the mobile TV is more the service than the technology.
Okay.
Just the idea of providing TV services to a handset. And then
Yeah.
what's the difference between a TV service and...
Yeah, for me, it looks like all the data, I mean the multimedia data resource, it comes from the server and then delivered to the customer. It's not much difference.
Sorry? Yeah.
I mean, these two, the mobile TV and mobile on-demand, I mean the stream, mobile stream, they are all sending the data from the server to the customer.
Yeah.
Right, so it's very difficult to understand what is the difference between these two technologies. Is it correct?
Yeah, that's why I say it's not.
Yeah.
It's not the technology that's so important.
Okay.
It's more just a matter of providing, a set of programs that you could tune into as if you were watching TV, but just doing it on a small,
Yeah.
on a mobile handset.
Yeah, but nowadays we are using more. I think it's more on-demand stream because we are
exactly.
iPad.
I agree.
So
yeah.
the concept of a mobile TV is not very clear to.
Well, and I think
Yeah.
that's why it hasn't been particularly successful.
Yeah. Okay.
The only reason I really introduced it was just because I thought there were these interesting kind of concepts that came up in the DVB-H solution that
Okay.
were worth just knowing about.
Okay. All right. To review your cost.
Okay.
Thank you. Thank you so much.
Thank you very much.
Yeah.
Thank you for asking questions and answering mine. It was nice to meet you.
We'll discuss if I have any discussion.
Yep, good on you. Okay, see you.
just realized, yeah, it's very difficult to memorize the content of the PPT, the lecture notes. So it comes to we have to understand everything. So through the understanding, we can write down like whatever
understand the logic
the thing,
yeah.
any topic, and when you ask something, probably we can't like fully rewrite everything from your note, but we can use our own understanding to describe the technology or.
It actually disturbs me when I see that people have them. I see some people use the exact words that were on the slides, and I think they haven't actually understood. They just.
But if for the exam, if you can memorize everything and write down exactly whatever from the note, but we still get a mark. Right? So depends on people how you want to choose the
Anyway.
well, right, thank you. I try my best to pass the exam.
Oh, I want better than a pass.
Okay. One question. When is the mark for the essay work coming up?
I'm working on it. It should be before the exam, yeah.
Okay,
But I'm not
it
sure.
will show up on the.
Yeah, it should be on the LMS, and I'll make an announcement when they're there anyway. Okay, good.
So also don't forget use my the one I sent you through email.
Yeah, I know. I remember. Okay, all right, see you.